we will continue with finite difference. So in the previous 2 hours, we have discussed how we construct a scheme for a desired derivative. First derivative, second derivative, does not matter what we are calling. We just focus on how we create it. A difference scheme, okay? So in this case, there exists in the literature, there exist three difference approximation. The first one is backward, forward, and central difference approximation. I'm writing here center, but it's central, guys, okay? Central difference approximation. So these are in the literature. We have already had these difference approximation, and we have mainly used them. Okay, so let's see here how we write down these forward difference or backward difference or central difference approximation, and what is the differences between them. We will discuss them at the end of this slide. We will also see here the main, I will list you the main schemes of the backward, forward, and central difference that we will use for solving boundary value problems. As well as this, I will also show you here an extra exercise to use at the number exercise. I will show you numeric exercise, okay, how we use forward, backward, and central difference approximation as the derivative approximation case. Okay, let's go in the expressions. Forward difference means that, look at here, guys, you locate yourself at the excite node. I am now on the excite node, okay? And then because of the forward, you can understand from the name, forward means that use your feature. So the feature approximation is corresponding to what? You are going forwardly. So it means that when you are writing here I'm writing here h, but does not matter. Sometimes it is delta x, sometimes it is also represented by delta notation. Doesn't matter what we call, but we know that this is just here the last point, right hand side minus left hand side divided by number of intervals. So after dividing it, it is corresponding to delta x or maybe h or maybe delta x expression. Okay, these are the same thing. So we are using here, because of the forward expression, you are using here delta 1 over, sorry, here is I plus 1 is used minus f of xi divided by h. So in previous we have observed as the delta x representation. Now I'm showing here instead of delta x, does not matter, it is like a dummy variable for you. Okay, when you are creating it, this is the forward approximation, okay, forward difference scheme. From now on, if I say you in the boundary value problem solutions, you will see what I mean, because generally we are talking about, we will use forward difference approximation now, or central difference approximation. So when I'm saying forward, you need to understand I'm locating myself at a point and I will use myself and also my feature estimation. So for this reason, this is corresponding to the forward approximation. Okay, to obtain the scheme, you can also use here the previous construction can be used also for this exploration, or we can just, I'm hearing guys, showing here, guys, just the verification. It is not a construction, it is just a verification, okay? So let us write down here the verification by using here the xi plus 1 means that what? F of xi plus h, because my increment is determined by h here. So for this reason, I'm writing xi plus h. I'm writing here the Taylor series expansion around xi, and in this second one, from the minus f of xi, there is no more expansion because there is no more increment that you have used. So by subtracting them, and you are having here the right side as in that one. What you want to get? You want to get here f prime xi here. So to get f of f prime xi, you should leave f derivative at xi alone. So you are getting here, your scheme will be as in that form. Okay, by the distribution, by doing the distribution, you are having here, look at here guys, f prime xi will become f of xi plus 1 minus f of xi divided by h minus h divided by 2 second derivative. What can we say about it? I'm choosing here my difference scheme, okay, and the remaining one will be does not matter minus or plus. Please do not focus on the constant. You are focusing on just your parameter, h to the power what. This is the thing that you need to write on the order of approximation. So here is h to the power something. The power arises because of the investigation, because I have multiplied 1 over h times h squared divided by 2. So it causes h divided by 2. So you are getting here, you know that because order of approximation is used, big O notation is already used. So I'm using here the equality. But if you don't want to write here this one, then it is turning to approximation with noting here order of approximation is corresponding to the power. H to the power 1 means that first order approximation because of the number is 1. Okay? Let us see the backward difference. Again, you are locating yourselves at the excite node. You're choosing a point actually. Backward means that what? You should use your previous one. The previous one arises as you know xi minus 1 then. So again the same thing. The backward formalization is given to you like f of xi minus f of xi minus 1 divided by h. Okay, so we are writing here again, you can do the same verification as we did in the forward difference approximation. You can do it and you will observe that here the order of approximation of the backward difference is again first order. This is again first order approximation. So does not matter whether you used here forward or backward place. This is giving you, because I'm using here 2 points, what's the problem? Is there any problem? No. Okay. So when you are using here the backward difference or forward difference, this is using 2 points causes first order approximation. Now we have a good thing which is so important in engineering fields, okay? Actually in applied sciences. This is so important method for us, which is called central difference approximation. The central difference approximation here, again I am using 2 points, but I'm locating myself as the middle point, okay? Now I'm locating myself at excite node and I'm using my feature at the same time my previous, okay, my history. So using 2 points and then I'm getting here the second order approximation. Let us see how the scheme created. So here is the central difference approximation scheme. You will see. Look at here. You have used your feature, your history, and also because of your increment here, delta x here or h, let me say, h one more time, 2h you are getting here between your points. So it is turning to 2 divided by 2h representation. So plus order of h square. Look at here. Now you have observed the second order approximation. So when you are using it, actually because we are passes through here, so I'm writing here f of xi also, but it is multiplied by 0 because I don't see here any f of xi here in my scheme. So this is multiplied by 0, so adding here 0 just, okay? So 1 times f of xi plus 1 here is minus 1 times f of xi plus minus 1, sorry, and here there is no f of xi, so because of this I'm multiplying by 0. Okay, now you are doing here the calculation. Don't forget this is now, I mean here guys, when you are using here the how can I explain, this part, okay, is not yet multiplied by minus 1. We just write here the expansion of f of xi minus 1 because it is what? xi minus h. So minus h is your increment. Because of this you are seeing minus h. Actually this is minus h to the power 2. Okay, and if you have one more operation here, plus minus h to the power 3 divided by 3 factorial and blah 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 and so on. So when you are multiplying them and by the coefficients, of course, as you can see here, so you are getting here the first derivative approximation you want to get. This is now, it is the process, so you can also follow these steps as we did in previous. So it's very easy for calculating them. And I'm trying to just obtain here the first derivative. For this reason, I'm leaving my first derivative alone. So when you are doing it, it is totally giving you what? This is now first term of the remaining part, so I can rewrite it like the order of h square because I'm focusing on my increment position. So the power of 2 gives you, denotes us here, it is second order approximation, which causes a good news. This is very beautiful news for us, okay? So we are considering here the central difference approximation. I have written here the error term for you, and this is your scheme of the central difference approximation. Again guys, I want to mention here, this is the time because one more time I need to repeat it. When you are using solving the boundary value problems, or mainly later on in your field, some of you will meet the partial differential equations, which is calling also initial boundary value problems. For solving them, you should, oops, bless you, you should use for the boundary value problem or any boundary value problem part of the differential equations, you should use central difference approximation mainly. Okay, so because of it gives you fast solution as well as more accurate solution because it is giving you two second order approximation. We also use, even though I'm using 2 points, okay? So 2 points forward, 2 points backward, but they gave you first order approximation. So again, I'm writing as a conclusion. This is our main important conclusion for the central difference approximation. Now guys, I will give here the table. This table is so important for our boundary value problem solution. Okay, we will use this table, I mean. This is important. Please, at home, study one more time this scheme. I will also write down one more time this one when we are going to do boundary value problem solution. We will discuss them. But let us write here as a summary for the finite difference approximation in the literature. So we have three different approximation for the difference in the literature: forward, backward, central difference. So the first derivative I can use for the forward difference, yi plus 1, which is used your feature estimation, and minus yi divided by delta x. Backwards means that you are locating yourself at ith node. You should use your history, so you are getting here the scheme. Central means that you take yourself in the middle of the interval, xi node, so I'm using feature at the same time my history, then I'm creating here my central difference approximation. For obtaining the second order derivative, don't forget guys, I am using, this is an important sentence for you. When I am using forward difference, backward difference, central difference, blah blah difference schemes to write down, to describe derivatives. Okay, so we are using numerical differentiation, which means that the difference algorithm corresponding to derivative. If there is no derivative, no difference approximation. Why zeroth derivative? Because defines you yi point. That's all. So the second order the second derivative can be observed by the forward difference. So you are getting here 2 points later, 3 points actually you are using, but you are locating yourself at xi plus 1, xi plus 2 divided by delta x squared. 1 minus 2 plus 1 here. Yi, you should use backward all the time, using the backward process, your historical background you should use. And then the central difference means that one is feature, one is history. It's coming from there. So this 1 to 1 actually, in the literature you also have the third derivative, fourth derivative, and so on. Okay, so the coefficients of these yi minus 1 or something like that, the parameters are coming from the Pascal triangle. So 1 3 3 1 in the next step, in this position you are getting here 1 3 minus 3 plus 3 and minus 1, like this one. Okay, so up to here, guys, we just completed the theoretical background of the central difference, forward difference, and backward difference formalization. Now I want to show you here a numerical example. Actually, in the face-to-face education, I did not give any time. I didn't give any question for the this type numerical exercises. But now, because of the distance education, you can not ask to me directly when you are meeting some like problem like this one. So for this reason, I want to give here one more exercise, which is numerical one for you. Okay, consider the function is given to you x to the power minus 2, 2x. Some points are chosen, 1.7, 2.0, 2.3, 2.6, 2.9. Find, now you will discuss here first derivative, okay, 2.3 by using forward, central, and backward difference formula. Let us see the points. First of all, I'm creating my table. Okay, this table is for the points and the values of that points in my function, because I need them. Look at here. If I'm writing here yi derivative, so you need to find out here yi plus 1. So I should write here yi, guys. This is important. Yi plus 1 minus yi. So you need to find out here your values of the function. Okay, here is the values of the function. And I'm writing here, for instance, if we want to use forward difference, where is your location? Location is 2.1. Now you are locate yourself at the point 2.3. What do you say? Forward difference. What does it mean? Forward means that what? I should use my next feature 1. So I'm using here my feature 1. Look at here. Feature 1 minus myself divided by delta x. Now we are writing 2.6 minus f of 2.3 divided by my increment. The increment here is what? 0.3. So by the division, you are observing here your expression as in that form. Okay, in the second process, central difference approximation. Oops, I have written here backward. Okay, so backward means that what? When I am getting here the backward difference approximation, we are considering here, let me choose another color. Okay, in the backward difference, again I set myself the same position 2.3 because I'm searching for the first derivative at 2.3. So, but what you say backward? Backward means that what? You should use your previous one, history. So, I'm going to the previous one, f of 2.3 minus f of 2.0 divided by the increment from here to here is what? 0.3. So you will do the calculation. Finally, you are getting that one. Okay, guys. Actually, up to here, by using forward and backward difference, I can say at that moment, I can say that these are first order approximation, so they are not accurate, which is as enough with the central difference approximation. I mean, you are considering here your second order difference approximation, which is central difference approximation, will give you the better solution. Let's do it and we will compare them. Okay, so we are considering the central difference approximation means that what? You will locate yourself to do again the same position, The same position says you what? Again, I'm here with my green marker now. I'm using. But what you say it by the central, use your previous and your future. Let's do it together. By the calculation, the answer gives you here, the central approximation will give you that one. So this is more close to your exact value. If you wish, you can also do it at home. And now I want to give here extra homework. This homework is not an obligation. It is just voluntary for you. Okay. Let me write here a question for you. Maybe this should be better for your studying if you wish. If you want to give me the answers for your answers to check my, I'm checking it. So it should be better. So then try to find out second order derivative, okay, second derivative by considering again the same point using forward difference, backward difference I wish to give here, and also central difference approximation. This should be better for your studying, okay? You will calculate them totally. You are getting me the answers. Of course, sending me the answers, sorry. Okay, so this part is over the numerical differentiation. From now on, there is no more case for you. I want to just summary what we did here. This part is so important for us for the numerical differentiation. Why? It is because of the solving numerical boundary solution of the boundary value problems. Okay, so to go there, we need to understand how we apply the schemes. Finite difference schemes, which is calling forward, backward, and central difference in the literature. And also, if we need to create another scheme which is very appropriate to our system or to our model, I can also create how I will create a scheme by considering here the Taylor series. Today's topic will be just on the numerical differentiation. So, guys, I'm closing at that point. So we will continue on the Canvas position, okay, on the Canvas record if you have any questions.